So lesson number 6, optimize RF conditions, radio frequency conditions, and performance for the clients. What we're going to talk about in this, again, this is another high-level chapter that introduces a lot of the different concepts that we're going to talk about. But, and we'll do a deep dive into these concepts when we get into the configuration of the controller itself. But really we need to look at how do we maintain optimal performance in our radio frequency environment. We know that the environment constantly changes. We get different RF interferers. The spectrum constantly changes. And that can affect client access and how the clients function in the network. Also, clients are mobile, right? They're moving around. They're associating to different access points. You will see the number of Wi-Fi devices continues to grow as well. They can be concentrated into specific areas at certain times of the day. So it's a very, very dynamic and ever-changing environment, which means it's really important to be able to dynamically manage that environment as well. Optimization for peak performance is absolutely required in the wireless network, especially when you start dealing with some of the higher data rates that we see as well, like 802.11 AC. So once we complete this particular lesson, we'll be a little bit more familiar with things like radio resource management, radio frequency groups, Cisco clean air technology, we'll talk about that, Cisco band select, client link technology, and just all of the different techniques that we use to optimize our radio frequency conditions and provide peak performance for our wireless network. You can see how this would be a kind of a pretty critical thing in the wireless environment. And Cisco does this very, very well. I would venture to say better than most vendors out there. In the past, wireless networks were typically just conveniences, right? It was a little add-on. You could have somebody in the break room working on their phone, or maybe a little computer on the internet and so on. But, and in those types of cases, best effort functionality was all that we really needed to concern ourselves with. But now Wi-Fi has been being used for rich media applications, integrated voice, video, business critical applications. So there's a term we use called RRM, or Radio Resource Management, that allows the unified wireless architecture to analyze the existing RF environment on a continuous basis and then automatically adjust things like power levels and channel configurations of the access points to mitigate things like noise from non-802.11 interferers, co-channel interference, signal black holes, signal coverage problems, that's what I meant to say, and so on. So RRM increases system capacity, provides automated self-healing functionality, and so on, to take care of dead zones and all kinds of things. So I always kind of imagine it as a juggler just juggling a whole bunch of different balls, and you push the juggler or you introduce a new ball. He's constantly adjusting, or she's constantly adjusting to that environment, and the balls don't always land in the same spot, right? So you're constantly moving around and making these changes. So even though RRM processes use information that's gathered by the actual access points, the APs kind of report this information. That's what allows us to make decisions on the adjustments to the AP's channels, the power settings, and so on. On a large scale, this is very, very important. It's kind of almost a necessity in that sense, because you can't constantly go out and monitor things and monitor your RF environment as an administrator. It just doesn't scale well. So it's a self-healing, self-sustaining type of environment, and that's what makes it very scalable. All right. Now, what does RRM not do? You can see it on the slide here. It doesn't substitute for a site survey for those initial designs. It doesn't fix your crappy designs, right? If you're implementing wireless incorrectly, it's not going to fix that problem for you. And it doesn't manufacture spectrum, meaning it doesn't provide you additional bandwidth or create these additional spectrum options. It's used to manage the existing spectrum. So it automatically detects and configures new controllers in lightweight access points as they're actually added to the network. So I take my 1700 or my 2700 series access point and I plug it in, it goes out and discovers the controller, it adds itself to the network, and based on its physical placement, all of the other access points around that access point gets adjusted and otherwise reconfigured to support the addition of that new access point, so we don't have overlapping channels and so on. Adequate coverage with the appropriate level of performance, and performance is always measured in the sense of throughput, to all users is what the primary goal is. So it may require that you deploy a whole bunch of APs. Of course, those APs have to operate on different channels. Those channels have to be selected intelligently so that they do not interfere with each other. We have some limitations on those channel assignments, right? Only 3 channels don't overlap. There's a feature within the controller that provides that, and that's the second bullet point that we see on this slide here, DCA, Dynamic Channel Assignment. Each AP radio gets a transmit channel assigned to it that changes if there are changes in air quality, whether there's interference on the channel or whether there's from non-802.11 interferers or even other 802.11 interferers. The level of network performance and, I guess I'll say unnecessary noise in the wireless environment is also directly attributed to the transmit power levels of the AP. I told you guys this a couple of days ago when we started this class. I said it's the solution in wireless for coverage is not to jack up the transmit power to the highest level. There are severe performance issues that can occur from that. So not only are we managing the channel assignments, we also have to manage the power that's being utilized, the amplitude that's being utilized for these different frequencies. Maintaining performance levels without contributing excess noise into the environment, essentially. We do that by managing AP power levels through the application of something called TPC, Transmit Power Control. There's an algorithm which runs on the RF group leader, and it monitors all of these access points, we increase power, so is needed, we decrease power as needed. Ultimately, what will actually happen is the access points will try to transmit effectively at the lowest possible power. As long as they can provide efficient connectivity to the clients, they're going to try and operate at the lowest possible power level. All right. There are 2 versions of TPC that exist, version 1 and version 2. Version 1 is typically preferred. Version 2, I know that's counterintuitive, but version 2 is only enabled under TAC guidance, and that's to solve lots and lots of strange things or problems that's going on in the environment, typically with AP density issues. All right. Whenever there's a change in the infrastructure, maybe an AP fails or it's been disconnected or whatever, that's going to introduce something called a coverage hole. It's like a little black hole, and everything kind of goes through that black hole and gets lost forever. So another feature that's built into this is the coverage hole detection and mitigation algorithm, right? Basically, it's just, hey, I detected that there's a hole in our mesh, in our wireless coverage. So what am I going to do? I'm going to change maybe how the APs around that coverage hole handle that space. Maybe I'll increase their power so that we increase the size of the BSA for that particular access point. Now, one of the things you do have to be concerned about when you're doing dynamic radio resource management and you're managing the network dynamically is you do need to be concerned about cascading change effects, right? I change one thing and then that ends up resulting in something else having to be a change and then another thing having to be changed and so on. So to avoid implementing constant changes that would keep the wireless network kind of in this constant state of flux, we usually, when we're doing our initial deployment, we turn off radio resource management. We deploy all the APs. We configure all of our settings, and then we will enable radio resource management. Otherwise, it's going to be kind of chaotic because we're adding new access points on the fly or ad hoc or whatever. Usually we like to wait, an hour or 2 hours, maybe 3 hours before we start to implement the radio resource management features. Once the network is stabilized, the anchor time and interval needs to be established to ensure that the DCA algorithm runs at least twice a day. And it's not something you necessarily configure. I think we just leave it turned on and let the controller handle that. We'll see when we do our wireless controller configurations how that gets configured and how that gets set up. Another important concept is an RF group. It's basically just a logical collection of Cisco wireless LAN controllers that coordinate information for the purposes of performing radio resource management in a global space, right? I don't want individual islands of controllers doing their own thing, because one controller might change one thing and that might affect access points that are connected to another controller, and then all of a sudden you have two controllers fighting against each other trying to figure out what the heck to do in the environment. So an RF group is created, and you can see it's depicted on the diagram here, to manage that 802.11 network. Clustering wireless LAN controllers into a single RF group enables the RM algorithms to scale beyond the single wireless LAN controller. All right? I don't know that we'll have a lab where you guys create an RF group, but when you do create an RF group, it has a couple of different characteristics. User configured group name. You can see in this particular diagram the group name is WAVE. Neighbor discovery that's performed at the radio level, so we're trying to figure out who's in proximity to whom and so on. The country list that's configured on the mobility controller, and then RF groupings that are going to run between the different mobility controllers. RF groups, mobility groups, they're very similar. They both really define clusters of wireless LAN controllers, but they're different in terms of how they're actually used. We know that an RF group facilitates things like system-wide dynamic RF management, but a mobility group facilitates mobility and wireless LAN controllers redundancy and failover. Controller software will actually, or the controller software will actually support up to 20 controllers, up to 6,000 access points in an RF group. The RF group members are added based on the maximum number of APs supported. The maximum limit for the number of access points in an RF group is 6,000. The number of access points that are supported is actually determined by the number of AP licenses that you're allowed to have on that particular controller. You can only have 20 controllers, including the leader, that can be part of an RF group, and then of course the sum of the access points of all the controllers is combined to be less than or equal to whatever that maximum limit is. All right? I don't think this is something you guys are going to run into too much in your environment. Send me a chat message if it's different than this, but I'm guessing you probably only have one controller in your environment. So radio resource management on a single controller is very easy. Obviously, there's not a whole lot of conflict there in that particular case. Okay? Let's see. Here's another diagram that kind of describes this process. You can see the RF group below, in the little circle below, and we have wireless LAN controller A and wireless LAN controller B. The group leader is very important in this architecture. The group leader is what analyzes all the real-time radio data that gets collected by the entire system. It's the one that's going to calculate the power, the channel assignments, and it's the one that sends that information to all the other controllers within the group. So only one controller is really making decisions based on that configuration. The actual RRM algorithm makes sure that we have restrained channels, power scheme changes appropriate to the different local RF neighborhoods, and so on. Lightweight access points do periodically send out neighbor messages over the air, and these access points use the same RF group name to validate the messages from each other. But you can see we do have different neighborhoods. Obviously, neighborhood A in this case is completely unrelated to neighborhood B in this case. Maybe it's a different building, or maybe it's a branch office or whatever. When access points on a different controller hear neighbor messages at a signal strength of minus 80 dBm or stronger, that's a very important number. Minus 80 dBm or stronger, the controller dynamically forms an RF neighborhood in automatic mode. So it actually groups these access points together into a neighborhood dynamically. You can do it statically as well. The leader basically just manually selects the members and adds them to the RF group. Each AP then complies and maintains a list of up to 34 neighboring APs per radio. So on the 2.4 gigahertz side, on the 5 gigahertz side, and then that information gets reported up to their respective controller. You can see that CAPWAP in neighborhood A, this CAPWAP or lightweight access point is actually reporting back to wireless LAN controller B, whereas these two access points are reporting to controller A. And then over here, subsequently in neighborhood B, this access point is reporting over to controller A. So the neighborhood doesn't really have anything to do with what controller the AP is associated to. But we do maintain a list of up to 34 neighboring APs. Each controller then maintains a list of 24 neighbors per AP radio, and from those neighbor messages that are sent, we can maintain that information. Once at the wireless LAN control level, so once I've gotten to that level, the per AP per radio neighbor list does go up to 34 APs. Then it can get pruned off. It drops to 10 APs with the weakest signals. The controller then forwards each AP neighbor list up to the RF group leader so that we can maintain that information. All right. The RF group leader can be configured to manage the APs in a couple of different ways. We already kind of talked about this in this slide here, but auto mode or static mode. In auto mode, the members of the RF group elect the RF group leader, and that device becomes the master power and channel scheme provider for the group. And then the RF grouping algorithm dynamically chooses the group leader and ensures that the RF group leader is always present. If the RF group leader goes away, then somebody else will be promoted to be the RF group leader. All right, static mode. The admin selects the controller itself as the RF group leader manually, and that's pretty straightforward. Okay. Usually we just run it in auto mode. It's typically pretty basic configuration. Another concept that exists is clean air technology. And like I said, on our YouTube channel, go out and check that clean air video out. It's an excellent video. Very, very descriptive on what this clean air technology does actually represent. Traditionally, when you look at a Wi-Fi chipset, particularly from the perspective of evaluating the radio frequency spectrum, the whole idea is that we're tracking all the energy in the airwave that can either be attributed to their own transmissions or something that can be demodulated as another 802.11 radio transmission. Any energy that remains in the spectrum that cannot be demodulated or really isn't identifiable as a transmit and receive activity, that gets lumped into a single category called noise. And we know that there are many, many things within a wireless network that can cause noise. The reality is that, and they found this when they were doing their research, that a lot of the noise is actually a remnant from collisions, maybe a Wi-Fi packet that falls below the receive threshold, so it's not processable. We can't really demodulate that information. But noise can come from a lot of other sources: microwave ovens, cordless phones, video cameras, Zigbee devices, all kinds of things, game controllers, and so on. To extend spectrum analysis even further, and at a much more granular level, by the way. When you watch that video, they talk about the difference between doing spectrum analysis with SE Connect and clean air technology versus a traditional spectrum analyzer, and it's just night and day, the difference. Cisco created this clean air technology. Clean air is a system-wide feature of a wireless network that streamlines this operation, right? In fact, it even offloads that processing of all that information. So you've got your non-802.11n traffic, all your noise, and you've got your 802.11n traffic, which is your client traffic. The chipsets that are built into these wireless access points actually are separate for processing the .11 traffic as opposed to processing the noise and doing the analysis. There's a chipset called the Sage that actually scans the spectrum once per second. If the Wi-Fi preamble exists, that information gets passed through the chipset directly and isn't affected by the parallel operations that the Sage chipset provides. So no packets are actually being lost during the Sage scanning process. That is really cool, right? Because that means that you can do full spectrum analysis without affecting throughput and flow from your clients themselves. All right. Now, the Sage does get disabled while a Wi-Fi packet is being processed through the receiver, but when in the times that the access point is not processing that data, the Sage is implemented. And we're talking about microseconds, times in between. You know, we talked about the different SIFS and DIFS time frames where we're not processing Wi-Fi data. All right. If you do get into the clean air technology, there are a lot of terms that you need to know about. You might see these terms on the exam as well, so we'll go through a few of these different terms. Spectrum intelligence, that's everything we know about the spectrum. All right. AQI, that is the air quality index. It's actually a number that falls between 1 and 100, and it represents how clean the spectrum is for sending and receiving signals. The higher the value, the cleaner the spectrum. Okay? There is an interference severity index that's called the SI. That's a way that we classify which non-Wi-Fi interfering sources are assigned. So we take all of our non-Wi-Fi interfering sources and we give them an SI value. And that goes into calculating this air quality index. That range is also from 0 to 100, but in this case, 100 is the most severe. You have the IDR, Interferences Devices Report, just a detailed report containing all the information about those classified devices. Very similar to what you would see in the Cisco Spectrum Expert Active Devices view if you've ever used SE Connect and access points in the Spectrum Expert application. Just a basic report. That actually gets forwarded to the MSE. MSE is the Mobility Services Engine, which does a lot more than just mobility, and then we can utilize that and the maps on the MSE to identify the location potentially of these interferers and so on. You've got the PMAC, good old PMAC, the PseudoMAC address. Analog video devices, cameras, whatnot, they don't actually have MAC addresses. We do still want to be able to track those devices, identify them, and so on. So the system generates kind of a pseudo MAC address that enables the system to correlate data about a single device by picking up that particular MAC address on multiple APs. Merge is a concept. They don't have it listed on, oh, they do there, PMAC merge. Yeah. Correlation of IDRs based on the PMAC database. Each AP essentially hears that an analog video interferer exists, and it independently generates a PMAC for that device. Now the idea is it's the same device. We don't want to identify that device multiple times as a different device. So the controller actually goes through and sorts all that PMAC information out from those multiple APs, creates this kind of device cluster, and even though it's the same type of device, we'll be able to merge that data. ZOI, the zone of impact. If you're looking at the heat map, if you will, you can see the zone of impact for a particular event. This is again something you would see on the MSE. And LMAP, the local mode AP. We also have monitor mode APs as well. We'll have a section later on when we talk about how to deploy different access points and what kind of methods we can use to deploy those different access points a little bit later on. With regard to clean air, though, these two, there are several different ways we can deploy an access point and several different functions it can provide. But with regard to clean air technology, these two are important. LMAP, local mode, and MAP, monitor mode. Within the clean air technology, the terminology, these are the two types of access points that can actually sense and report interference data. So you do want, we'll look at later on when we're configuring the wireless LAN controller how we can select the actual access point mode. A local mode AP, obviously, as you can see here, serves clients, whereas monitor mode APs, their whole purpose is to scan the spectrum and identify any interferers in the spectrum. By the way, monitor mode APs do not serve clients. They do not transmit active neighbor messages. They don't show up in neighbor lists, and so on. So they're simply there for monitoring the spectrum. All right. The goal here, healthy wireless environment. All right. So it is going to require a little bit of knowledge about what types of interferers can exist, where they exist, and you have to understand spectrum intelligence. So spectrum intelligence is definitely a core technology that's designed for proactively managing this wireless spectrum. It's all about RF activity, and Cisco has integrated a lot of algorithms and a lot of technology into this clean air architecture so that it can dynamically identify and work with these environments. So it provides that visibility to all the users of that shared spectrum, both Wi-Fi and non-Wi-Fi interferers. For every device that operates in the unlicensed band, ISM, 900, 2.4, and 5 gigahertz, what is it, right? Where is it? How is it affecting my wireless network? So this is a really important concept. Spectrum management is the active use of spectrum intelligence. Clean Air provides that spectrum management technology. Okay. I mentioned briefly Severity Index, just an algorithm that runs on a Clean Air AP. It's calculated for each classified interference source, and the index is structured from a range of 0 to 100. 0 means that I have the least impact, 100 means the most severe impact, and the Severity Index directly influences all of the other calculations, specifically the AQI calculation. Remember I said AQI 100 is the best and 1 is the worst in the air quality index. Severity actually applies to each individual interfering device. Air quality is an inverse relationship, but it really represents the severity of air quality over the entire channel, over the entire band, the floor, the building, or the campus. All right, so how is the severity index calculated? It's based on really signal to noise ratio, right? What is the power level of that device? Sometimes we call that duty cycle, relevant to the Wi-Fi signal. So the louder an interfering device is, or the higher the duty cycle, the higher that index will go. By the way, duty cycle means how often are we seeing those frequencies. 100% duty cycle means it's constantly interfering with that channel. Severity also includes CCA thresholds. Basically, a CCA threshold is where the interference really starts to be disruptive. So we might be able to identify interferers, but maybe they're not. The signal to noise floor is relatively low, right? So it's not really affecting the wireless, the Wi-Fi traffic. All right. All righty. As I said, the air quality index, that's more of a measure of the spectrum as a whole, as opposed to looking at individual devices. It's basically just a concept of characterizing air quality based on all the SI information that we're collecting. All energy within the spectrum that is definitely not Wi-Fi has to be accounted for, and we have to classify that information. So the system actually interprets energy that's modulated as 802.11 traffic, and it classifies that energy as co-channel energy or adjacent channel energy. For all the classified devices, the system then calculates the severity index, like we talked about on the previous slide. That gets an integer from 0 to 100, and 100 is the worst. That index is then subtracted from the air quality scale. So 0 to 100, with 100 being the best, to generate the actual air quality index for that particular channel, for the AP, for the floor, for the building, or the campus. It's a rolling average, right? It indicates the impact of all the classified interfering devices against a theoretical perfect spectrum. And these are values that you can see in MSE and the wireless LAN controller. PseudoMAC, I kind of talked about that. We have non-Wi-Fi interferers that we can't easily track or identify. They're not sending anything that, from a data standpoint, that's identifiable. So the ability to identify those types of transmitters that lack those unique identifying characteristics is really important, and it's a very, very key component to the clean air technology, because we have the ability to apply a label or identify these non-Wi-Fi interferers. We can identify the location, the zone of impact, and by correlating all the AP reports and isolating unique instances and looking at the time counts and so on. Because an analog video device doesn't actually have a MAC address, or for that matter, any other identifying digital tag, there was an algorithm that had to be created to identify those devices being reported from multiple sources. So as part of that device classification, this PseudoMAC is calculated, and it's included in the IDR, the identity of the device. Each AP then generates this PseudoMAC independently. They're not going to be identical, of course. They're going to be similar, and then we start doing all of our comparisons and evaluating those PseudoMACs, and then we go through the merge process where we merge that information. Okay? Another key component is band select. Right? Now, we're not talking about channel selection. We're not talking about choosing an individual frequency. We're actually talking about, do I use 5 gigahertz? Do I use 2 gigahertz? Whatever, all right? This has become more and more prevalent because obviously now devices tend to support both bands without a problem, especially with 802.11n, 802.11ac, and so on. Obviously, the 5 gigahertz band tends to be a little bit less used because there's such a large proliferation of 2.4 gigahertz devices. A lot of devices still actually prefer to attempt to connect at 2.4 gigahertz. But a lot of devices also support 5 gigahertz as well. Okay? And in fact, you'll find that a lot of the interferers that you see in wireless networks still operate in that 2.4 gigahertz space. So how does this band select feature work in a dual band capable access point? When a client is attempting to associate to an AP, the client sends out the probe request, and it sends it on all channels looking for a response so it can proceed with the association process and then the authentication process and so on. In this particular case, let's just say the client is a dual band client. So it's actually sending out probes on both frequency bands. The controller can actually identify it and mark the client as dual band capable. So when sending the probe response back to the client, it will send it on the 5 gigahertz radio immediately and then delay the response on the 2.4 gigahertz radio. Obviously, the goal here is to encourage the client passively to join the 5 gigahertz radio because it didn't get an option yet to pick the 2.4 gigahertz radio. This is a feature that you can enable globally on the wireless LAN controller, or you can do it for a particular wireless network if you want. All right. We briefly discussed Cisco Client Link, just a proprietary technology that Cisco developed to focus on mixed client networks with the goal of optimizing the overall capacity of the network, making sure that our 802.11an and our AC clients operate at the highest possible rate in these mixed environments. It enhances MIMO antenna characteristics of our modern APs as well. What happens is we take advantage, and I described this when we talked about Client Link a little earlier, takes advantage of the multipath propagation of the radio signal to maximize the signal to noise ratio wherever those legacy clients are located. So we get additional throughput, we get higher bandwidth, basically about 25% greater throughput for our legacy clients or our slow clients than we would normally see. All right. So we did talk about the Client Link technology before, and I think you guys have a good understanding, but it's something that's typically enabled for legacy clients to increase their throughput. In 802.11n and 802.11ac systems, we can actually take advantage of the multipath by sending multiple radio signals at the same time. That's that multiple input, multiple output technology. So each of those signals, which are called spatial streams, get sent from their own antennas using their own transmitters. Because there's space between those antennas, each signal follows kind of a different path to the receiver. That's, if you recall, what we called spatial diversity. If the receiver has multiple antennas as well, each with its own radio, they can independently decode those arriving signals, and then those signals can be rephased, they can be combined together for upfading, and so we take these multiple data streams and we receive them at the same time. All right. What are some of the features of Client Link 3.0? Transmit beamforming, we talked about that. Improves downstream performance through and throughput to the clients. Really focused on mixed client networks. Also adds support for standards-based explicit compressed beamforming feedback. Say that 10 times fast. Explicit, I can't even say it twice. Explicit compressed beamforming feedback, ECBF, so that we can get feedback on the strength of the beam and how these beams are being sent to the clients. Primarily for 5 gigahertz, since 802.11ac is a 5 gigahertz standard, but also available for other standards as well. Across the clients, different wireless standards are used. We know that we see A, we see G, N, AC, and so on. AC being the one that's going to provide the most performance for the devices. But we can increase the performance of that if we add these spatial streams and the spatial diversity. A and G clients can kind of mess that up, right? They can hinder the performance of these AC clients. So within a mixed mode environment, legacy clients like A clients and G clients, and kind of N clients today, have different requirements for connectivity. So the Cisco Client Link feature allows us to handle that. The tables that you see here basically show the evolution of the Client Link technology from 1.0 to 3.0. 3.0 is available on the 3700 series access points. 4 distinct transmit antennas to enhance the performance of that mixed mode environment. Increases the downlink signal to noise ratio and the data rate over distance. Reduces coverage holes, enhances the overall system performance. All right, so we see the number of transmitters to improve reliability. In the case of the 3700 is 4. Clients supported, all of them, the number of clients supported per radio and so on. There's another chart here that's kind of an extension of that as well. And some of the features that are covered and some of the features that are not covered. As you can see, Client Link 2.0, Client Link 3.0, very, very similar to each other, right? Nobody really uses 1.0 anymore. The only difference with 2.0, not supported with AC, yeah, the 3600, 2600, 1600 series access points. All right. So that wraps up this this chapter here, this module, or this lesson, I should say. Talked about radio resource management, what dynamic channel assignment is, what transmission power control is, what coverage hole detection and mitigation is, those algorithms that allow us to manage our radio frequency spectrum, RF groups, if you do have multiple controllers, clean air technology, band select, client link, and so on. And there will be other lessons that we will have that will go into even more detail on some of these technologies a little bit later on. So next we're going to get into, in the next lesson, we'll wrap this one up, but the next lesson we're going to actually get into the layer 2 infrastructure and how do we support connectivity of our controllers, of our access points through this layer 2 network.